This is GCSE Physics Unit 8, Waves and Sound, and I've split it into two parts. The first part is about waves and the second part is about sound. So energy and waves. Waves carry energy from one place to another. So it's not the movement of particles themselves, but just energy. So we define waves as the movement of energy from one place to another without the movement of the particles themselves, or without the displacement, maybe is a better idea, without movement of particles. Now they do vibrate about their own position, but they don't actually move from one place to another. So there are two main types of waves you need to know. They are transverse and longitudinal. And examples of transverse waves, well, I'm going to do longitudinal first. The main example of longitudinal waves is sound. And that's the one you really have to remember. Transverse waves then could be anything from light. You could describe water waves, any of the electromagnetic waves such as X-rays, ultraviolet, microwaves, radio waves, and so on. They're all transverse waves. And so you can see a light here, and then this is meant to represent sound. Okay, so we're going to talk about transverse waves then. If you make a transverse wave using a rope between two people just like this, and I'm sure you've done this quite often, or you've done it with the slinky spring in the classroom, what type of energy is the wave transferring? So as you move your hand up and down at this side, then the rope moves up and down, or the slinky moves up and down and passes to the person at the other end. So of course, because you're moving your hand up and down, that's kinetic energy. In which direction is energy moving? So it's moving from, if you start here, then it's moving from left to right there. In which direction is each part of the rope moving? And if you have a look, there's already an arrow put on here. I hope you can see that. And the arrow is moving up and down, and we'll just maybe draw it on here, one of these places where it's a bit lighter. So it's moving up and down there. And therefore, it's moving in this direction. And we're going to draw this using a ruler. And I'm going to extend it a little bit. So it's moving up and down like that. And if you have a wee look at and compare the direction of the movement of each part of the rope to the direction of movement of the energy, you can see they're at right angles to each other. I draw a wee right angle in there. And so this brings us to our definition of a transverse wave. So our definition of a transverse wave, the definition is that the particles move. So the particles which through which the wave is moving. So the particles move perpendicular to the direction of travel of the wave. Or you could say to the direction of travel of the energy. I'm putting it in brackets just. Alright, so whenever we draw our waves here, we draw lovely transverse waves like that. Nice even waves. And you can see that the particles are moving up and down about their own position. They're not actually moving from here. So if we have a wee particle at this point here, it doesn't move the whole way down to the end. It doesn't get down here. It just moves up and down about its own position, and as energy passes by, all the particles are going to move up and down about their own position in a direction perpendicular to the direction of travel of the wave, like that. Okay, so we're going to label our transverse wave now. And we label various things about them. The first thing we might label is a crest, which is the top part of the wave, or the place where there's a maximum displacement. So displacement is movement out of its rest position, up or down. A trough then is at the bottom. Now a couple more things that we might label. We might label a wavelength. And a wavelength is from one position on one wave to exactly the same position on the next. And I'm going to label it here from a crest to crest, but I'll show you other positions that you could label a wavelength in. The symbol for wavelength is lambda, and that's from the crest to the crest. It could be from a trough to a trough, or it could be from any position on a wave to exactly the same position in the next. Now what we say about those two positions is that they are in phase with each other. So if you're going to choose a position there, you can see that, then the place which is in exactly the same is not here because this part of the wave is moving down, but this one's moving up. It's the next time that the wave is moving down in the same position, and therefore it's over there. And you should find that distance, and we'll just measure it using the ruler here. So it's approximately 9 centimetres, and that should be the same as this one here, and we'll just check. Yeah, it's approximately 9 centimetres, 18 up to 27 there. Maybe you can see that better there. So you can see that no matter where, if you have got an even wave like that, then you should always be measuring the same wavelength at any part of the wave. Now one more thing which isn't shown there, and we'll use black to do this, I hope it'll come out, is the amplitude. And the amplitude is from the middle or the rest position up to the top of a crest or down to the bottom of a trough, and that's called the amplitude. Sometimes you're given some information about a wave and you're told that its displacement from top to bottom is 10 centimetres, but that's the whole thing. And if you're asked for amplitude, then you have to divide that by 2. So just be careful. It's a very common mistake that lots of children make.